Hi and welcome to another video for Year 9 Additional Maths. This time you're focusing on the chapter on series, which is about progression. So in the previous video, you have learned how to deal with arithmetic and geometric progression. So for this subtopic, you are going to deal with what if in the geometric progressions or geometric series, we are dealing with infinite geometric series. So this one, you have to use the condition for the convergence of a geometric progression. That means it will converge or it will go towards a specific finite number. And the thing that we'll use for O-level examination is how to find the sum to infinity for a convergent geometric progression. So this is the formula. S infinity equals to A over 1 minus r. So where a is the first term and r is the common ratio. Okay, so let's begin. So say if we have a geometric series, okay, so let's say for this particular geometric series where the first term is 2 and the common ratio is half, so what happens in an infinite geometric series is that the terms will be continuing forever. So here, as you can see, when you look at the terms in continuously, so here you will see that they are added, but the terms that you will deal with towards the end of the terms over here will be much smaller than 1 over 8. So for this series, it can be shown that s1 equals to 2, sum of the first two terms is 3. So here sum of the first three terms is 3.5, and so on. So this one, if you see, the number keeps increasing, but it will approach the number 4. So here, this is the visual representation of the series. So you begin with 2, and then as you go applying the common ratio of half, you will have a 1 over here, and then half of 1 is a 1 over 2, 1 over 4, 1 over 8, and so on. So this one, if we add them together, you will have a rectangle with total areas which approach the value of number 4. So this is the sum to infinity idea. So this is an example of convergent series because the sum to infinity converges or going towards onto a finite number. So here, this one, consider this geometric series for this general formula. So it will be A, and then A times R is AR, and then AR times R is R square, and so on until you get to A to the power of R, AR to the power of N minus 1. So here, this is the formula that we had learned previously about a sum of a geometric series, which is A bracket 1 minus R to the power of N over 1 minus R. If, say, if the R is between -1 and +1, so if you try to make the power into a larger and larger power, so the R to the power of N will obviously get closer and closer to 0. So here, let me give you an example. So let's say, using the previous one, if R is half, so R to the power of N, let's say we go to R to the power of 10. So here you will have half to the power of 10. So here, let's say half to the power of 10 would be this number, which is already a very small number. So you can see here 9.76 times 10 to the power of 4. So if we try to increase the power of n, let's say it becomes r to the power of 100. So here you change the power of r to the power of 100. So from 9.76 to the power of 10 to the power of 4, you will get something much more smaller, which is 7 times 10 to the power of -31. So there's a lot of zeros in front of the 7, so which means it is approaching the number 0. So here, as n approaches the infinity number, so the r to the power of n will approach 0. So if you have infinity n, so the r to the power of n will be considered as 0. So that's why we get this formula of the sum to infinity of n of a geometric series, which is a to the power of a over r minus 1. But the biggest condition for this one will be provided that r is between 1 and negative 1 and so on. So here, let's have a look at the example. So here, if we have the first three terms of a geometric progression, so this is your u1, which is a, and then 15 is u2, and 8 is u3. So how do we find the common ratio over here? So the common ratio are, it is easy to use the second term divided by the first term because they are of consecutive terms. So this one, the r will be 15 over 25. So therefore, if we simplify r is 3 out of 5. And for part B, how do we find the sum to infinity? So sum to infinity formula will be 1 over, a over 1 minus r. So let's recap back. Okay, a over 1 minus r, provided that r is between negative 1 and 1. So here, this is obvious that the r is between negative 1 and 1. So let's proceed with the sum to infinity. Sum to infinity equals to 25 over 1 minus your r, which is 3 out of 5. So this one means it is 25 divided by 1 minus 3 out of 5 will be 2 out of 5. So this one is finally, this is your sum to infinity, which is 62.5. Okay. Alright, so this one is the sum to infinity, 62.5. So let's move on to the next example. So here, at example number 2, a geometric progression has a common ratio of negative 4 out of 5. So this is your r, negative 4 out of 5. And it is given that the sum of the first 4 terms is 164. So this is S4, which is 164. So the first question is, how do we find the first term of the progression? So now what are we going to do here is use the given information that we have here. So you have the sum of the first 4 terms already and also the common ratio. So here it's quite obvious that we have to start with the formula for the sum of a geometric progression. So sum of a geometric progression, for this one, it will be n equals to a bracket, it should be 1 minus r to the power of n over 1 minus r, because here the common ratio is between negative 1 and positive 1. So let's put in all the numbers. S4, n equals to 4, so 164 over here equals to the first term, okay, because this first question is to look for the first term, a bracket 1 minus, the common ratio is negative 4 over 5. So let's put in the negative 4 over 5 to the power of, because n is 4, so 4 minus 1 is a cube. So this one over here. So let's close the bracket over 1 minus negative 4 over 5. So let's have a check here. I will try to simplify this on 1 minus negative 4 over 5 bracket cube first. So let's see what will happen. 1 minus bracket negative 4 over 5 and to the power of cube. So this one is 189 over 125. So here 164 Okay, apology for the mistake. It's now here the n is power of 4 because n is 4 over here. So let's double check. So here it should be 4. So 369 over 625. So let's double check again. Okay, just to make sure that we all have those correctly. So yeah, so the first one is next to A, it will be 369 over 625. 625. Okay, 625 over this one, 1 minus negative 4 over 5. This is just, I just put power 1. So this is a 9 out of 5. So next to A is would be 369 over 625. 369 over 625. This is divided by 9 over 5. So this one next to A will be 41 over 125A. So obviously here you have to multiply with the reciprocal of the fraction 41 out of 25. So I just write down 125 times 40 times 145 over 41. So here therefore my A is 164 times 125 over 41. So this one is a 500. So there you have it. This is the first step. Okay, for the next part, B is to find the sum to infinity. Sum to infinity, just to recap back, it is A over 1 minus R. So this is my reference. In order to remember this easily, just have to make sure that this is 1. So your A is a 500 over 1 minus R is 1 subtracted by the common ratio, which is negative 4 out of 5. So this one, if we use the calculator, so just type in 500 over 1 minus bracket a negative of 4 over 5. So this one will give you 2,500 over 9, or I can just change this into a mixed number of 277 and 7 over 9. So this is the sum to infinity for this geometric progression. Okay, moving on to the last one. So here you are given a question where the first 3 terms of a geometric progression are given in expression. So here this is your A, which is your U1, K plus 15, and then this is your U2, which is K only, and K out of 12 is the U3, the third term. So how do we find the value of K? So over here, you somehow have to create a formula for to find the value of K. So over here, one of the idea that you can use to find the value of K is by using the common ratio R. So as per you have recognized just now, it is the second term divided by the first term, or the third term divided by the second term. So over here, I will write down U2 over U1, which is your A, or you can also use U3 divided by U2. So here, if we just focus on the terms, so this one, U2 is a K over K plus 15 equals to U3 divided by U2 is K minus 12 over K. So this one seems doable, so let's have a look. Okay, so here, since you have a single fraction on both sides, you just cross multiply the denominator into the numerator. So the left side is a k times k, which is k squared, equals to k minus 12 bracket k plus 15. So this one, you can expand the k minus 12 times k plus 15. So I will have k times k is k squared. 15k minus 12k is a plus 3k. And then negative 12 times 15 is negative 180. So this one, you can see the k square exists on both sides of the equation. So if I move the k square to the next side, it will be k square minus k square, which will give you a 0. So this 0 equals to 3k minus 180. So 3k is positive 130. So therefore, your k is 180 divided by 3, which will give you a 60. So from there, you can identify all of your terms. So let's rewrite it down. So your u1, which is your a, is k plus 15. The k is 60 plus 75, 15 will give you 75. Okay, u2 is your k. K is your answer from the part A. So k is 60. And u3 would be 60 minus 12. So 60 minus 12 is a 48. So from here, you can already proceed to finding the sum to infinity. So let's have a look at the sum to infinity. So sum to infinity requires you to use a over 1 minus r. So here, the first term is 75, but we haven't decided on the 5 yet. So r for the common ratio, the r is 60 out of 75, which is u2 over u1. So 60 out of 75, if we simplify this, it will be 4 out of 5. So here, if we want to double check, 48 over 60 is also 4 out of 5 if we are dividing the u3 by u2. So the sum to infinity, here it will be a is 75 over 1 minus 4 out of 5. So this one, 75 divided by 1 out of 5, which will give you 75 divided by 1 out of 5 is 75 times 5, which will give you 375. This is your sum to infinity for this particular geometric progression. So with that, that's the end of this video. I hope that it can help you in filling in your notes. So with that, thank you very much and see you in the next video. Thank you.